Welcome to Pomodoro Joe for Tuesday, July 11th, 2023. Today we're doing LeetCode problem 863. All nodes distance k in binary tree. This is a medium problem. All right, so given the root of a binary tree, the value of a target node, target, and an integer k, return an array of the values of all the nodes that have a distance k from the target node. You can return the answer in any order. All right, that's pretty straightforward. So we have an example here. Looks like our target node is 5, and we are, let's take a look. Input is this, target is 5, k is 2. Target is 5, distance is 2, so that's 1, 2. That gets us to 7, and then 1, 2 gets us to 4, and then 1, 2 gets us to 1. So 7, 4, 1. All right. And then we have some constraints. Okay, so let's put 25 minutes on the Pomodoro timer and we'll get started. All right, this one's going to be tricky. So we'll start with a result, set it to some list because we need to return a list of the values of all these nodes, and we'll return the result at the end. All right, where do we go from here? Well, so if we were only to try to find the nodes of a distance k below our current node, that would be pretty easy because we could just do a recursive function that traverses the tree below this node and finds nodes that are a distance k away from this node. But the fact that we have to traverse back up the tree, well, that's pretty much impossible in a binary tree. Once we get to this node, we don't have any information about where it came from in a traditional binary tree. So I think what we need to do is we kind of need to convert this from being a binary tree to being something that we can traverse in different directions. And that would be a graph, basically. So once we get to this node 5, then not only do we have our paths down, we could have paths back up. So we need to convert our tree into a graph. It's not trivial, but we can do it. Now, if you've watched my other videos, oftentimes when we're given graph type problems, we are given pairs of nodes that are connected, and then we build our own graph list or our own dictionary of connected edges. So we'll kind of be building that same dictionary here, only we'll have to do it from our tree. All right, so let's have some node to edge list here, or map. All right, and this will be a default dictionary of list. All right, and I'll just make a note here that the key is our node. Maybe I'll make it a node value. That'll make it easier. Okay, so the key will be the node value. Well, let's actually make sure that node values are unique. I didn't check that. We have between 1 and 500 nodes. All the values are unique. Okay, so we can store just the value. Cool. So our key will be the node value, which is the representation of our node, and the value will be a list of connected nodes. And that's directly connected, so that's kind of like our edge list. All right, and then we need to build it. Oh man, so we could build this using a stack or a queue. I think I'm gonna build this using a recursive function just to make it easy on ourselves. So let's do a build graph. And this will take our root node, and then it will build all the connections, all these node to edge map connections from that root node. All right, so this is going to be a recursive function. The first part is our base case. That's if this root node is none. So if we don't have a root node, then we'll just return. So we will actually be building just into this directly. So we won't actually have return values. So we can just return, we just exit out. All right, what's next? Let's see. If our root node has a left, then we'll add our left and the root node to our node to edge map, and then we'll recurse. So if root node, all right, so if there is a root node left child, then we'll do this node to edge map for the root node dot value, because I'm using values here. and we will append the root node's left node. Let's see, root node dot left node dot value. All right, so did you get that? It's a little tricky. So we're just saying for our node, this root node, which is represented by the root node value, we will add an edge to the root node's left node. And again, it's represented by the left node value. And we have to do the same because we want these to be bidirectional. We don't want them to be one direction or directional. We need to have the reverse of this. So essentially we have to have the root node dot left val, and we'll append the root node's val. All right, so now this edge goes both directions. And then we need to recurse. So this is where we do our build graph on the left node. Cool. So we add our edges to the left node and the root node itself, and then we'll also have to do the same for the right node. All right, so root node right. If we have a right node, then we'll add the right node's value here. And we'll add the root node to the right node list. And then we'll recurse on the right. Cool. All right, so now that we've done this, let's actually just call it, and then we'll print out the result just to see if this is working. All right, so we'll call build graph. And we'll pass in our root node. And then let's see, we'll just print our node to edge map. All right, so let's just see if this part of our function works. And it doesn't. Result is not defined. I misspelled. Try that again. Cool. So we're not getting the right answer, but that's expected. What we're getting for our default list, we have 3 is connected to 5 and 1. That looks right. We have 5 connected to 3, 6, and 2. 5 is connected to 3, 6, and 2. Awesome. 6 is connected to 5. Great. 2 connected to 5, 7, 4. 5, 7, 4. All right, this is looking really good. Awesome. So now we have a graph. We no longer just have a binary tree, we have our graph. All right, so now that we've converted our tree into a graph, we can start doing a graph traversal. Now this is going to be our standard graph traversal. We can do breadth first search, depth first search, doesn't really matter. I think in my case, I'll do a breadth first because I think if you do breadth first, you'll end up getting these nodes closer to the time that you start, but I don't really know. All right, so for our standard breadth first search, we'll have some queue, and we need to start our queue with our node. So our node here will be our target node. So we're going to start at the target, and we'll be traversing all of the edges to find all these nodes that are at distance k away from our target. So we start at the target and we work our way out. All right, so our target node, and we need the target value because we're representing all of our nodes by their values. And then we need to give it a distance. So we're going to say it's distance 0 from the target. All right, what else are we going to need? Well, typically we'll need some visited, so I'm just going to create that here. So we'll have a set of our visited nodes, and we'll start with this, but we might actually need to keep track of which nodes are already in our result so we don't end up having duplicates, but we'll see if we need it. All right, so while we still have some nodes in our queue, we'll grab our node and our distance out of this queue. And I will do a pop at 0. So that's a breadth first search. All right. If the node is in our visited, we'll just continue. Otherwise, we haven't seen this node. So let's just check the distance. So if this distance is equal to k, then we know that we are k distance away from our target, which is exactly what we're looking for our result. So we'll just result.append this node. And we can continue. Because we know that we've already traversed to this node, we don't want to go any further, so we can just continue. We'll just skip to the end. All right, now if this node is not distance k from our target node, it probably will be less, which means that we need to add its connected nodes to our queue. So for every connected node in our node to edge map, for this node, all right, if that connected node has not been visited, then we will add this node to the queue for processing. Let's see, I guess this will be node and the distance plus 1, because we're taking one more step away from our target node. All right, and at the very end we do return our result. Okay, so this should work. I'm a little bit uncertain about whether or not we might end up with duplicates in our result. I don't think we will, because we're checking if it's visited here before we append, but I'm not 100% sure. All right, let's give this a shot. So this is sort of a two-step approach. Step number 1, convert our binary tree into a graph, and then step number 2, use our typical graph traversal, in this case it's a breadth-first search, to find all the nodes that are distance k away from our target. All right, let's try it out. Connected node is not defined. I missed the C. I typed too fast. And we are getting lots of duplicates. Look at this. We're getting our target node as the duplicate. That's interesting. Oh, because I'm not adding it to visited. That's a silly mistake. So if the node is in visited, then we'll continue. If it's not in visited, we actually need to add it to visited. All right, but the fact that we were putting 5 in there in the first place is strange. Now, I guess we were probably toggling back and forth. That's probably what happened. All right, let's try this again. Now we're not returning anything. All right, what's going on here? This was a dumb typo. We need to put the connected node into our queue, not the node. That's what happens when I name things too similarly. Okay, let's try this again. Okay, so that seems to work, and it looks like we don't have to worry about our duplicates. Let's do our own test case though before we submit this. I'm just curious. Let's say we're trying to get to 6 and a distance of 4. So that means we're here. We have to go 1, 2, 3, or 1, 2, 3, 4. All right, this seems to work. Let's give it a shot. Hey, and it works. All right, we do okay. We beat 46% for runtime and 59% for memory, so that's not too bad. All right, let's jump back here really quick, see if there's something we can do to speed this up just a little bit. I'd love to get above 50%. What can we do? We could try to make this a deck. That often works. Let's give that a shot. So a deck is a double-ended queue. And you can basically just replace your list with a deck, and it should be a little bit faster. It's good at pushing and popping elements. So let's do this. We will pop left on our queue. Try that. All right, so that gives us a little bit of a boost. So we're at 65% for runtime and 35% for memory. So we take a hit in the memory, but we do better in our runtime. All right, there's a couple things we could try in here. One, we could try to make this not a recursive function. We could do our build graph as an inline function or an iterative function. That might save us a little bit of time. What else could we do? Instead of doing this continue, we could say if node not invisited. Sometimes this helps. Oops. So we're going to say if node is not invisited, then we'll indent all of this. We'll add it to visited, do this. Okay, so that might save us a little bit. Let's see. Oh, that's a huge savings. So Skipping the continue and putting everything inside the if block, we get up to an 82% for runtime and a 59% for memory. So that's awesome. All right. You can play around with this code a little bit more, see if you can get this above a 90%, but I think that's all I got today. So check this one out. Again, this is LeetCode problem 863, all nodes distance k in binary tree. All right, again, just to solve this problem, we broke it down into pieces. Piece number 1, convert this tree into a graph. Piece number 2, do a breadth first search on this graph. We could try, actually, we'll try doing a depth first search, although I don't think this is going to make any difference. Nah, takes us back down to 54%, so we did better before. All right, so I'm going to put this back the way it was. All right, so yeah, play around with this one. It's super fun. All right, hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.